All right. Well, welcome everyone to LayerOne. I know you guys are probably coming back from your lunchtime food comas, but my name is John, or a lot of you know me as ArcLight. I know I decided to be all bold and use my real name here. You know, this presentation, it's kind of a scandalous, shady thing to do. So today we're going to talk about access control systems, and by access controls, I mean physical security controls, like these RFID cards we're all been issued to get into our rooms. Possibly a poor choice in the Marriott's part, I don't know. So what we're going to do is sort of go through this. We did this exercise over a period of about 18 months. We run the 23B shop hackerspace. That's a lot of y'all are going to come down there tomorrow maybe for a party. But we got tired of dealing with metal keys, and we started looking into researching an electronic access system and realized that there were kind of a lot of things wrong with that from a hacker's perspective. So for starters, why are we doing this? So security and access control systems, they're mostly closed source and very proprietary. We really had a hard time getting much usable information from any of the vendors. Very little of the information about their inner workings is published. Some of them publish a little bit about their external protocols. There are some NEMA, some IEEE standards, and an alarm manufacturer standard for eliminating false alarms and a few things, and ANSI stuff. But that's really about it. Some of them even have their chip numbers scrubbed off, and their ROMs with the fuses blown, so you can't read anything out of them. We need an access control system. We basically got tired of dealing with keys and having to sometimes let the landlord in, not being able to revoke keys if we gave one out for somebody. So we decided we want electronic access controls, and we want something that we owned, that we could prove how secure or insecure it was, and we would be able to modify it. So in order to really get there, I think it helps to start by defining what we mean by security in this case. So this is the classic Bruce Schneier or Ross Anderson security engineering triangle. Security defined in terms of assets. In our case, we're not talking necessarily electronic assets, data, but we're talking about people, we're talking about our facility, our stuff, maybe our information inside there, maybe our server room. We're talking about threats to those assets, threat actors, actual people who intentionally want to get to you, harm your stuff, vandalism, theft, all those sorts of things. And then we're talking about countermeasures, things we can wrap around those assets to provide some sort of mitigation of those threats. And important differentiation, safety and security are related, but they're not the same thing. Security is typically the countermeasures you install to mitigate intentionally harmful threats, whereas safety, that more encompasses things like human error and natural disasters, but they affect each other, and sometimes doing things like adding safety systems increases security and vice versa. One other thing to consider, all of these things have trade-offs. We talk cost, convenience, and we have things like the creation of new vulnerabilities. We're all familiar with that maybe from doing web security and network security, but when you're talking about things like making sure you can exit your building in case of a fire, it kind of acquires a new dimension. So we have to, look at that. Things that are open the doors, let's say an emergency, shouldn't be able to be easily subverted to open it for an attacker. So there's something kind of interesting. Ross Anderson, Security Engineering, it's a great book. He has a good section about physical security, and he really kind of formulates it. There's a kind of a four-sided square, four-sided figure. The four things you can basically do with physical security devices and countermeasures. You can't stop anyone from getting into your stuff or your facility. That's just not going to happen. The four things you can do, though, are deter them. You can delay your attacker. You can detect an attack after it's already in progress or being attempted, and you can mount some sort of response to it. And that response could be anything from communicating with your attacker with an intercom, setting off a siren, calling the police, paging the guard desk, anything like that. So fundamentally, these are all there to enforce a security policy. And that security policy is something that you have to decide for yourself, whether it's your apartment, your hackerspace, your corporate high-rise, what are the priorities and what are you really trying to get out of this? just like an enterprise IT security policy is necessary before you start buying firewalls, you need to figure out what procedures you want to be enforced by your access controls. And some pretty fundamental ones that come up over and over: security and safety of the personnel. Any kind of security measure you put in that does not protect the people who actually work in the building, give them something, they're not going to follow. They're going to prop the door open, or they're not going to care, because it's apparent that their safety isn't first and foremost in mind. Prevention of theft or damage to your assets, that's a big one, and auditing of access and security events. That sort of stuff falls back into deterrence as well as response. It lets you mount a response after the fact, maybe prosecute someone, maybe find a vulnerability that you wouldn't have from the logs. And when we talk about threats, something that's kind of interesting, there is a model developed. It's in some of the security textbooks. It came from an Army officer. They don't cite the name, but they basically come up with 4 model attackers. And this is something I haven't seen. Obviously, we have the model attackers in the room, but they all fit the same mold: black shirts, kind of shady looking. This is a little more formal. What they did is they came up with these 4 arbitrary guys, and I say guys, but that's what they did. We have Derek, Charlie, Bruno, and Abdurman. And these guys sort of represent a spectrum of different threats, physical threats to a facility or some assets. And the first one, this is probably the biggest one we had in mind with our hackerspace security system, Derek. Derek is a 19-year-old addict. He's looking for a low-risk opportunity to steal something he can sell for his next fix. Rather fitting, because we're also 1 block away from a methadone clinic. Yeah. Hackerspace real estate isn't always the most prime. So our next one, we have Charlie. Charlie is a 40-year-old inadequate with 7 convictions for burglary. He spent 17 of the last 25 years in prison. This is like your classic career con. Although not very intelligent, he's cunning and experienced. He's picked up a lot of lore during his spells inside. He steals from small shops and suburban houses, taking what he can to sell to local fences. And this is a guy who, may do a smash and grab, or might be someone who has access to some more sophisticated things, some tools. Maybe he can do some lock picking or lock bumping. Some of the things that you might see in a residential or commercial burglary, repeated over and over. And then we have this one. This is kind of interesting. Bruno. Bruno is a gentleman criminal. His business is mostly stealing art. As a cover, he runs a small art gallery. He has a Ford University degree in art history and 1 conviction for robbery 18 years ago. After 2 years in jail, he changed his name and moved to a different part of the country. He has done occasional black bag jobs for intelligence agencies who know his past. He'd like to get into cybercrime, but most he's done so far is stripping 100K worth of memory chips from a university's PCs in the mid-90s when there was a memory famine. And then our last one, this is something that, the kind of elusive threat that's always in the news, but you never seem to see, Abdurman. And Abdurman heads a cell of 12 militants, most with military training. They have infantry weapons and explosives with PhD-grade technical support provided by a disreputable country. Abdurman himself came out 3rd in a class of 280 at the military academy of that country, but was not promoted because he's from the wrong ethnic group. He thinks of himself as a good man rather than a bad man, and his mission is to steal plutonium. So clearly we have different kinds of threat actors. We don't really worry about the last one. That's the military's problem. Really, it's sophisticated controls wrapped around lots of mass, things like concrete barriers that stop trucks and explosives, and detachments of Marines with guns who come and kill those people. And the first one, second one, those are the problems of criminologists and sociologists and so forth. So we really are kind of worried about Bruno. He sort of fits in the upper end of off-the-shelf criminals. That's what we design things like data centers and higher security installations around. But we probably don't design every business around that. So I travel to a lot of businesses, and we talk about enterprise security and things like that. And I've kind of made some observations. Your typical business perimeter is protected by your standard 5 to 7 pin mortise lock from Schlage, Yale, Sargent, et cetera, tempered glass windows, an alarm system. Typical kinds of stuff we see. Larger sites have electronic perimeter access controls often, and they're in many cases tied into building systems like HVAC and lighting and maybe an on-site security desk that monitors it all. And the physical, mechanical locks they have are usually higher grade, like Best and Medico and some of those brands, mostly for key control and the ability to master key a little bit more safely. This kind of thing, it represents good basic protection from burglary. It meets insurance requirements, and the Derek and Charlie threat models are probably covered fairly well here. Data centers, high value merchandise handling facilities, those are geared more towards the Bruno attacker, where you have things like defense in depth, layered security, not just a perimeter, a more robust detection response, maybe with armed security from a security company that has very rigid protocols for not taking no for an answer if they call back and things like that. So some of the typical features of these, looking into these, we took apart old alarm systems and access controls, and we looked at existing installations where people gave us permission. And we typically have modules that control 1 to 4 doors, little black boxes on the wall here and there. We have a centralized, usually Windows platform computer that stores the access token information and keep logs. They typically push out policies. Usually you can access the doors and so forth without that system being on. It stores it locally in case that thing goes down. We usually have some sort of access device. You're talking, where the rubber meets the road, an electrical signal between 5 and 48 volts is what's going to open your door. It's typically an electromechanical device. Things like an electric mortise lock, which we have one here, I'll show you. Door magnets, we'll have some pictures of those. And you've probably seen those a lot of places. They're a big heavy-duty electromagnet that holds the door shut. Electric strikes. If you ever get buzzed into a pawn shop or somewhere like that and you hear that horrible sound, that's usually an AC-operated electric strike. All the stuff that we're doing is basically ending in closing some kind of relay and energizing a device that was invented in about 1910. Gotta love it. The access and token readers, early systems used things like plain pin pads, and they used physical keys that turned a switch. And now we're looking at more things like cards. It could be magstripe, contact cards, smart cards, contactless, RFID cards, that sort of thing. EM4100, those are cheap open standards. RFID cards are used in less expensive systems. The HID systems are basically a slightly extended protocol with a few more bits, at least on their lower end. MyFair and Dala, some of those brands are able to do things like read and write data and do a little bit more stuff. Some important things, almost every facility has some sort of device that gives anyone a free exit. There might be a push to exit in the appropriate local language, maybe it's lit up. They often have motion detectors, actually usually both. In fact, usually the push to exit physically applies or interrupts power so that if all that electronics is not working, you're still able to get out. Sometimes they have a button that you push it and a little egg timer goes off for, counts down 30 seconds and lets you out to make it inconvenient so that you don't use that as your main means of getting in and out. They may have integration with some centralized console application where security cameras can follow the events. The camera comes up immediately in the loading dock. If a motion detector goes off saying that there's a truck there or someone pushed a button to the intercom. Most facilities have the capability of doing a remote lock, unlock. It could be something dumb like go to my PC, managing that Windows PC. That's kind of scary, but that does control physical access sometimes. You do have things like a guard console that they can verify that you're at the right door with a camera and then let you into the loading dock without having to leave and go track the guy down and open the door. And then integration with the alarms, anything from just triggering a contact to full IT level integration. So I went ahead and made a little diagram, kind of shows how those work. In a bigger facility, you'll typically have the access servers in some sort of database in a server room, and they're basically just answering SQL requests and some kind of front-end software. They could be clustered or not. Typically a management PC, and smaller systems, the management PC is also the database and the policy pusher. We have things like HVAC and alarm systems. A lot of the newer ones have Ethernet built in and the ability to communicate with these things. Sometimes there are integration software companies that tie it all together with a PC application. And we look in the lower left-hand corner, those little panels, sometimes they come as bare boards, the cheaper ones do. A lot of times they're a little sheet metal box that the electrician screws to the wall in a closet somewhere, hopefully one that locks. They have a UPS because you don't want to get denied access to your space if the power is out. They typically have a simple microcontroller. It could be an Atmel or a PIC or some other type of CPU, and then some kind of network capability. The older ones are RS-422, basically a fancy serial port that goes over long ranges. Newer ones are all starting to be Ethernet based. And those doors, they have a few elements. They have things like an access reader. It could be a pin pad, a scramble pad, where it's a fancy pin pad that's harder to shoulder surf. Some type of token reader, so something you have. It could be a biometric, which is basically taking your fingerprint and something that it thinks is your fingerprint and giving you some numbers that compares against the database. Typically a local copy of that cached there, and then requests further can go back to the access server. And then they have what they call a rec sensor. That's request to exit, basically a button or sensor or both that let you out, regardless of what state the door is in and so forth. And then they typically have a sensor on each side to see if someone's actually there. And sometimes those decisions are handled locally, and sometimes they go back to the panel. But in any case, there's almost always a mechanical override or some sort of way of getting people access through that door, at least in the exit direction. The systems that do block your physical path to exit and don't have an easy mechanical way of opening usually have to have something like an integration with the alarm system, fire controls, things like that, so that they can get a signal to release all the exterior doors, let's say, in the event of an emergency. Something that needed for safety codes. NFPA has, I think they call their Part 101 that governs that, but also something that can be subverted by an attacker. Again, all our newer systems, they're going to have an Ethernet network, preferably a good secure one, but if it's installed by an electrical vendor, it may just be some done Netgear hubs and that sort of thing. So we can talk about the threat model a little bit. We talked about some attackers. What are advantages and disadvantages of these electronic locks? The first and foremost one, the business problem they really solve, it's easy to revoke the keys. The keys are cheap, they are disposable usually, and you can give them and you can electronically revoke them without any real financial penalty. Obviously hard to do with metal keys. You can have very flexible security policies. You can make your front door or any door in your facility or any space accessible only in the context of a certain time of day or week or month. Your physical location in the facility, security level that is assigned to you, security policy. You can have public and private areas with different policies wrapped around them. You can have, for instance, alarm sensors everywhere, but you can choose to not alarm but only log if it's a lobby during business hours. You can maybe have it make a decision just like you would analyze logs and do an intrusion detection system for IT security. You could determine if someone's there in a certain hours that they aren't supposed to be there. You can raise an alarm, do things like that. Public spaces often become private spaces on the weekends or after hours, that sort of thing. One nice thing, it can be a good hedge against carelessness. So it can do things like allow the front doors to always be locked, even if people are there and so forth, because you can make it very convenient to swipe in and out and unlock it. Whereas in the system you might have had before with mechanical locks and metal keys, those are going to be just something that always gets left propped open and left unlocked. And you can also use alarms and things to discourage that. And the last thing that's really important that you don't have with mechanical devices, you can audit it. You can know not necessarily who, but at least what token was presented or what alleged user accessed what and where. and what path they took through it if you comb through the logs. And finally, a lot of your stuff, anything from lighting to alarms to air conditioners, they can all be tied into this. Ethernet and dry contacts where you just have an on-off relay or sensor. You can do things like turn the air conditioning on or turn the lights on ahead of someone coming into the facility so that their security is actually improved by having their path lit and through the parking lot or through the space. And you're also saving energy and making things more convenient. So let's talk about the disadvantages of electronic locks. We're kind of here to think about security measures in terms of how can I break this, right? We're all hackers. So RFID, right? That's been big in the news. It's been big everywhere. I know a lot of you people I've seen in the audience probably built the Proxmark. It's like a Swiss Army knife that can decode and even emulate these cards. What do these cards do, right? If we fundamentally look at it, it's a little radio antenna with a chip on it. And when you put it up to a reader, it can be interrogated without having to necessarily touch it. And it can spit back an ID, or it can make some sort of transaction where data is stored and rewritten, or a challenge response is done or something like that. And they're designed to be basically used like a credit card at contact distances. And it's assumed also that they aren't going to be readily cloned. Well, it turns out we know that's not exactly the case, right? A physical key can be cloned. If you get physical access to it and you have a key machine or access to a locksmith. It can even be done with a high-res photo. That was proven in a paper in 2008. But these RFID cards, they have some problems. This technology is really only meant to be read from a few centimeters away, but depending on the system, you can build larger coils and power them up with more power. And you can do something like read an RFID card from a foot away or even 5 feet away, possibly. If you ever walk through a shopping center that has the anti-shoplifting tags, that big plastic stanchion in the middle of the aisle is a box full of big coils that are maybe 15 centimeters across, and there might be 30 of them. And they will pick up those low-frequency tags that are on your goods and alarm if you bring one out. Well, that sort of thing can be adapted to read RFID cards in an unauthorized way. So we like to say if it can be read, you should just assume it can be cloned. If we accept the premise that these are just chips, they can be emulated with software. And we have some very fast microprocessors and microcontrollers that can basically bit bang out any type of signal you want. Another disadvantage, they require electricity. And in requiring electricity, we have some interesting new problems that come in. For one thing, power can be interrupted or can be manipulated. Like we can do things such as analyze the power going to a device and maybe deduce whether it's sending zeros and ones or processing something or possibly get to spit out its key. We might be able to short it out and interrupt its power and deny use of that reader or that door. We might be able to, if the system is poorly designed, get the door to open by applying a high voltage or drawing down the load and making it brown out, different things like that. Unlike a physical lock where basically those tumblers and metal bits moving around are governed by physics, this is something that if you can control the power going to it, you may be able to do unintentional things with it. And finally, they might fail in an unpredictable way. A door lock is probably just going to break if it's vandalized or abused too hard, but you don't exactly know what an electronic device with a few thousand lines of code you didn't write is going to do when you possibly push it to fail. And another thing, if you want to try out, let's say, every Medico key there is, it might take you a year of sitting there with tryout keys, even if the tolerance is a little sloppy. But in a poorly designed system, you might be able to hook up a device or a widget that can basically let you try all those in seconds or minutes. Now, its strength is also in that because it's software-based, it can have countermeasures to that, but it's certainly a real attack that's possible. And finally, you are depending on the security of everything in there from the physical layer through the network in order to get that signal safely to wherever it's authorized, your token is going to be authorized, and back, and that authorization signal the same way. can be good or bad. So with all that in mind, we set about designing an access system that we could use to research these issues and that we could use for our space. So we came up with some criteria. First, we felt that relevance to the Derek and Charlie attackers made sense, and really our main goal was keeping the junkies from our alley out of the shop. The original door control was a Schlage deadbolt with 5 pins. So we figured if we can beat that as a security target, we're at least better off than we started. Resistance to a more sophisticated attacker, always a plus. Sorry? So we need to control 2 doors. Most spaces are smaller. Places have a couple of spaces, maybe a front and back door. We felt that was a good starting point. When we get to something with lots of doors and so forth, we're probably looking at something that's going to be multi-tiered and have those distributed modules anyway. We like the idea of being compatible with off-the-shelf readers. So we've seen a few RFID projects. The DOS Labor Space in Germany, I believe, did some very interesting homemade readers and ported crypto code and hand wound the coils and made some really neat devices. The problem is, though, we felt that would be a little bit hard to replicate. We'd prefer to get something that's low cost and off the shelf so that other people could pick this up and hack on it. And the other thing that kept coming up, there were people that got some really fancy, interesting widget like a Hearst scramble pad or some type of retinal scan or other biometric that was surplus that got discarded from a renovation of some high security facility, and they figured out how to make it work. That's great, but if someone else were to try and pick that up, they'd be $5,000 each new, just for the system with no manual. So we thought that wasn't really as relevant. We preferred something you could get either used on eBay as a commodity or new from, pick your knockoff vendor. We like the idea of being able to run independent of a PC or other, server. Anything with a real OS has more ways to attack it. It has millions of lines of code you didn't write. And if we divide it into what we call hard and soft tasks, hard tasks mean things like opening and closing the doors, and soft tasks mean things like connecting to the internet, which require a lot more sophistication. We'd rather the soft tasks be allowed to fail and not affect the hard tasks like leaving the front door open. Kind of a basic embedded systems philosophy that the dumb device is the master and the smart device is a peripheral. And of course we want to do logging and auditing. That was debatable whether it could be internal with a flash card or PC based. Turns out we can do both. And we want to have alarm and sensor capability, be able to detect occupancy so we know when someone's there. Have maybe 4 or more alarm zones for alarm and occupancy detection and request to exit, things like that. And we also like the idea of being able to integrate with existing alarm system, with a contact, so forth, so that we have some redundancy and defense in depth. So we came up with a methodology. We decided to start with the Arduino. It's a microcontroller that, kind of lowest common denominator, ground floor for embedded systems. And it appeared to have enough I/O ports and processing power and storage to do this. We wanted to have time and date security policies possible to implement, multiple security levels, need to be very physically robust, battery backup, protection against reverse polarity and high voltages and all those sorts of nasty things that happen in the wild as opposed to in your breadboard. We want it to be low cost, so open standards tokens and readers, adaptable to new stuff, something we could build for maybe $100 or less. Commercial systems, there are a few China knockoffs, but most of them you're looking at $1,000 to $3,000 per door to electrify. So that's kind of out of the budget of your starving hacker. And we want something that was repeatable. Only commodity components you can get through DigiKey or Element 14 or Mauser or, God forbid, Radio Shack. Cell phone shack. So we took all those constraints in mind and started designing something. We put it on a breadboard and we started testing some free code we found for interfacing to some of the readers and that stuff. We had to do a little bit of debugging. There's something called the Wagon protocol, which is Wiegand or Wagon, I don't know. Zach Franken actually did a talk here in 2007 about how to intercept that and replay the tokens and so forth. But between that, some manufacturer's data sheets, we figured out how, how that works, and we got some code together. We built a 1.0 version of the circuit board. We put some basic input protection and a UPS power supply on there. We found some RFID cards that are used very successfully in industry for things like cattle tracking and goods and things like that. They are available in keychain and swipe card format. It's called EM4100. Some are rewritable, some are read-only. So we got our hands on some of those readers, and the tokens were less than $1, so affordable to play with and cut them up and so forth. And we assembled it all on a piece of plywood and called it version 1.0. So this is it. There's a power supply that's not very efficient on top with a UPS and a big honking battery. There's a couple pieces of door hardware. There's a door magnet on the bottom. There's our board in the middle, or just up from it. And then there's a couple of readers. A mullion reader, which is basically designed to go on basically the door jamb edge next to a front door. And then there's an interior reader that has a pin pad, so we can use two-factor authentication or send some commands, that sort of thing. And so we sort of treated this like it was the front door. So every time someone would come in, we would swipe in and out and test it and try to break it, find out all of its flaws. And we used that with a homemade PCB that we didn't spend much money on and kind of refined it. We found out some things like the Arduino Ethernet module takes a lot of power and can burn up the regulator on board, some of them. So we made a nice 1 amp switching power supply and put that on board. We decided to make it carry 5 amps continuous current for some of the heavy-duty, high-security door hardware you can get. Put in more protection in the inputs, made it harder to reset and brown out and all those sorts of things. And we sent off a PCB to get created. And we went ahead and built in some capability where it can store 200 local users, 255 security levels, added a console you can control via Ethernet, and or rather via serial, but it can also be serial over Ethernet. And we integrated alarm and access functions and tested the snot out of them, and of course some self-testing routines. And this was the result. So this is our first commercially produced. It's kind of big for an Arduino shield. It's about 6 Arduinos worth. And it's got some big relays and a switching power supply in the middle. That's that. Input protection with surge protectors, m4vs. It's got big screw terminals. It's got some Darlington transistor arrays. A lot of this is stuff we copied from 1980s alarm panels. We figured, that's something that's been used and abused for 20 years. So they probably were doing something right. And then we put a real-time clock on board, something Arduino doesn't have. And we opto-isolated everything, so there's no direct connection into that micro. So its little world is, hopefully sandwiched away where, bad people can't get to it as easily. And we tested with that, and we are now at our, I guess we call our 2.11, and we have a basic piece of hardware that supports 2 readers, supports any of the compatible Arduinos. We tested with the Freeduino and the Seed and a lot of those. It's interrupt driven, very responsive on the reads. It does have remote monitoring capability. We're using just serial to a small Linux PC now. We looked into using the Arduino Ethernet, and it has a lot of issues. It's single-threaded, and it doesn't respond very well when, let's say, your host hangs up and needs a full 30 seconds to time out, and during that time your front door is open. Not so good. So the hard and soft tasks, we figured that should just be offloaded to a wall-wart, Linux PC or an embedded device of some kind. And we kind of fine-tuned the remote administration, put in a console password, and 3 strikes you're out for an hour and things like that. And we published the EagleCAD files and the Arduino code and packaged it all up. And then we decided to eat our own dog food. We put it in production. And we secured some commercial door hardware, which is pretty expensive, it turns out. If you have a storefront type building anywhere in the US, it's probably equipped with an Adams Rite aluminum mortise lock. And they're the only game in town, and they want $300 and up for their stuff. Residential doors, there are some cheats for that. You can hack those little Schlage keypads and stuff to just be a dumb solenoid for the door. But we programmed it up and installed it in an old alarm enclosure we gutted and put a big honking battery, the big honking battery from before in there. and a little UPS circuit, and a nice 5-amp power supply that's mil spec. And we started putting in here and plumbing up all the stuff. And it's worked out pretty well. We found about a dozen major bugs the first week we had it in production, including one that would let you enter any arbitrary command after a successful swipe, even if you were not the right person. Some stuff like that you don't really find until you live with it. And we installed all this nice hardware, put a little bit higher security locked than that Schlage 5-pin that was in there before. And we have a couple options. Some of our doors, this is at another site. This is a magnet lock with 2 magnets and a request exit reader. This is one we installed at another door. This is your door magnet. It's about a 1,200-pound pull magnet. It only takes about 200 milliamps to keep it shut. And then there's a Bosch exit reader. You see this thing over and over. If you do see one of those in the wild, by the way, you can pull that cover off and you can do things like change the pattern that it picks up from and make it more permissive. You can set the sensitivity to be higher so that things like waving a sheet of paper through the door crack will let you in. Something to think about. So in doing all this, we started finding some vulnerabilities. This is really why we're here, right? First of all, the wiring. Wiring is absolutely vulnerable in any of these systems. A few of them do have full challenge response capability and encryption between all of the devices and the brain or the authentication panel or the access server, but most of them don't. So you can do things like man-in-the-middle, that Wiegand protocol. You can have a device that stores and replays successful swipes. You can short out the low voltage wiring that controls the solenoids. In some cases, if it's not designed well, you might be able to blow a fuse and have a not a fail secure, but a fail safe door open. That's device right there, that door magnet, when you interrupt power to it, it opens no matter what. So if you can attack the wiring, you can blow a fuse or you can cut a wire somewhere, you're in. We also found something else interesting. Some of these devices have a little 1 or 2 wires that are grounded to indicate a green LED, a successful swipe, or a little chirp that you got in. Well, some of those are tied into the same relays that control the doors. And if you can backfeed that, you can supply your own 12 volts, or you can short it to the power to the reader. They might backfeed that door hardware and let you in. So something interesting. And we also figured out that the alarm sensors, most of our alarm systems are pretty good. They have usually a resistor in there somewhere. If you were to either short out the wires or cut them, both those will trigger an alarm. But some cheaper systems that just use digital pins, you might be able to just short out the alarm wiring and have it improperly read that the door is closed when it's really open, that sort of thing. And we also figured out another nasty attack that's probably feasible on any of these is applying high voltage, something like a stun gun or plugging it into 110, probably will just blow up a component and just disable that reader. But you don't know if they don't have good surge protection like fast TVS, transient suppression diodes, and MOVs and stuff. If that can get on the power bus and into the microcontroller, you might be able to cause something unpredictable to happen, like a register to get set high that opens the door. It's not predictable, but it could happen. Now the tokens themselves, the readers, we discovered that, of course, anything that you contact physically, it's vulnerable to vandalism, to being unscrewed from the wall and manipulated. You can obviously vandalize it or cut wires and do denial of service. Of course, you can clone RFID and other tokens. You may be able to do replay attacks, and skimmers are a valid threat. That's something that actually could be totally passive. You could have a little overlay that's powered by the field that powers up RFID cards when they're present, and you can use that to maybe power a skimmer and store those tokens. And you can use the reader's own field. We also discovered that most of these readers have no collision protection. So meaning if you have 2 or more tokens physically within range, it can't read either of them. Or it may read the first one and then go into like a lock state where it won't accept a second read. So you could glue down an old token conceivably and deny access to that reader. Interesting things like that. Also, we alluded to this before, but very few systems have any kind of protocol security. It's clock and data or weekend or serial data. Really not anything that can't be trivially spoofed, replayed, intercepted, passively or actively. The systems that do have this are usually used for things like transit tokens, security, secure payment systems. Even the ones like the mobile speed pass that have encryption have had papers published where they're alleged to have been broken. So I don't think anything that relies on a master key, something like that, should really be considered secure. Some of these access tokens, they all come in different formats. They have key fobs, they have implantable chips, that's the lower left-hand corner, wallet cards. Typically, the larger the device, the longer the range it can be intercepted at. So the small devices have actually some additional security in that they don't work very well at long distances. Harder to power them up and get them to read. The classic HID token everyone has, this is actually very similar to these knockoff RFID chips that are used for industrial applications, but it has, instead of 26 bits, maybe 34 bits in the key, but they're very similar interception technique. So the physical hardware, we also found there's some things you can do, like those door magnets. Typically, they're stronger than the door frames themselves, but it turns out that putting a piece of paper or a piece of tape over that magnet reduces its strength dramatically. Sort of an inverse square thing. It's actually possible to put like some heavy clear packing tape or contact paper over it that looks either clear or same texture as the magnet, and it reduces the door strength, the holding strength about 90%. So it'll look like it's closed, but you can kick it open. Kind of interesting. There are some door strikes, maybe not very well made, non-ferrous materials. Any of those are possible to attack physically and destroy, but some of those may have the possibility of putting a strong magnet, like a hard drive magnet, up to it and subverting it. Might also be possible, if it's not well shielded, to induce a current in its magnetic solenoid strong enough to open it. And then this is the classic one. Some of you guys may have used this to get into a data center or somewhere when you lost your key or whatever, but the exit readers are almost always installed insecurely. There are some guidelines like keeping the push to exit button 6 feet away from the door jam and things like that. They're never followed most places. Maybe they can't be because it's a narrow hallway or whatever. But motion detectors can be fooled in a number of ways into opening. You can throw something through the door, you can inflate a Mylar balloon under the door crack, heat it up with a hairdryer. You can access the buttons with a special tool bent out of some heavy wire. All of those are possibilities. And almost always the security policies are implemented in such a way as you want to prevent false alarms and not worry about absolute prevention of someone getting through the exit sensor. So I thought it might be interesting to bring some hardware. Everyone likes to play show and tell, and maybe demo the system. We do that? Oh, good. Okay. All right. So what we have here, we have our version 2.11. That's the current version of the access control. And this guy has a couple of different sensors attached to it. Here's a Mortis electric strike. And we can do things like take an unauthorized card. We can swipe it. We just get a beep. We can take an authorized card. We can swipe it, and our little solenoid retracts. It actually opens. Tells us it's open. This other one, this is a commercial HID reader. We can do that as well. We can activate it. We have something else kind of interesting. We have a cloner here, and we can clone one of these chips. This is a $50 eBay find. It literally has a coil of wire, a couple capacitors, and maybe 3 chips on board, just a little AVR micro. And if we take a card here, like this one that's not valid, we put it up to the coil, we read it, and then we take this rewritable tag. This is called a Q2. Put that on there. Takes a little longer, but now it's cloned. Okay, doesn't let us in. That's fine. Now if we take this valid key, which we can see does let us in, we can read that. Takes just a second. We can clone it. And now we're in. So I see there's really no reason this couldn't be installed, I don't know, let's say in a bus bench or, Starbucks that day traders, like to hang out in or whatever. So, if it can be read, I believe it can be cloned. You should operate without assumption. And then this wiring, obviously along the way, this is just very small gauge, 22 gauge wire, something like that. These aren't pushing a lot of current. And it doesn't take a lot to, you have to be very diligent about protecting this stuff. Kind of interesting. We don't have all the alarm outputs and everything hooked up to this, but you can easily put 4 different zones of alarm sensors in, and you can expand that more with shift registers or resistors or different other ways of doing it. We do have 4 open pins for Ethernet or additional sensor stuff. So just a little bit about that stuff. While we've been doing that, we also have been logging this. So this is our serial logging. It's really simple. It's just 57 kilobit serial over USB. And we can send that into a Linux log host that tails the logs. We have some scripts written up that are published. Let you do things like pipe that to an alerting system or email or SMS you when someone comes or goes or an alarm happens. Really basic, but it gives you the capability of directly internet monitoring or via cell phone or modem what you have. And we have those 4 relays, only 2 of which are used for the door. So one of those can easily go into our alarm system as well and trigger the alarm monitoring company. So just the last thing, again, we have our physical exploits. We have the capability of potentially manipulating the wiring, doing horrible things with the data in transit, intercepting it, replaying it. We can do denial of service in a number of ways with these things. The contactless readers, in some ways, are better because we can put all of our reading behind the glass or inside our perimeter, but we have, obviously new problems with being able to intercept it out of people's pockets and lunch boxes. So if you are curious about, the engineering behind that and how you can predict how much range you can get and how much power, I actually was able to find one engineering textbook on RFID that's on here. It's our 3rd entry down, this RFID handbook. It's translated from German, so it's a little bit weird. But it gives you a lot of interesting info. And I highly recommend this book, Security Engineering by Ross Anderson. This really has everything from physical security to building secure embedded systems to secure networking. Pretty neat stuff. And the last book on the bottom, there's some interesting projects in there that you can implement as just a hobby hacker type RFID toys. This guy, Amal Grafstra, actually implanted an EM4100 chip in his hand and wired up everything from his car to his house to open from that. So there's someone who's been living with it. Pretty interesting. And we have a few good links too. The protocols for some of the stuff are published. The man-in-the-middle attack that I mentioned, that's Zach Franken, DEF CON 15 and LayerOne 2007. We have some of these documents from the CSAA, and it's basically an ANSI working group, and some other stuff about smart card vulnerabilities, and some other interesting stuff about just threat assessment in general. The last thing, we can download the code. Everything, the Eagle files, the design, the Arduino source code, it's all right there at that Google code link. And does anyone have any questions? Yes, sir.
Logging keyed access.
Logging keyed access. So that's kind of problematic. The best you can do is log that the door opened a certain time. Some of the door hardware has a specific sensor inside that is tripped in the event of a key physically turning it. But that's something that depends on the mechanicals. Really the only reliable thing is determining the state of the door or the state of a motion detector outside of it. We call that a request to exit if it's on the inside, and that generally is logged in most of the alarm systems where they are actually correlating someone tripping that sensor with a request to exit. But they'll let you out regardless of whether you trip that sensor. Anything else? Yes, sir.
Integrating with the the alarm system, have you found any, let's say in residential or commercial, any legal issues with that, or any insurance issues or things with integrating with, like, say, ADT or something like that? Is their hardware even capable of being integrated with easily? to
So
alert?
yeah, the easiest way to make that happen is to basically ask for a dry contact loop. Most of the alarm vendors are okay with giving you an on-off contact that, turning that on or breaking that connection will trip the alarm. People use that for things like, let's say, monitoring their freezer if you have a grocery store. You want the alarm to go off if the freezer quits working so that you don't lose $10,000 worth of seafood. And you can get it for, like a sensor that detects if your basement is flooded. So generally they're friendly with that. I don't think they care so much what's on the other end as long as it doesn't put high voltage in or screw up their system. That's what I found.
It's a pretty common thing then.
Yeah, it's a pretty common thing you can request. The smaller systems may not have enough zones, or the systems they give you for free, I wouldn't count on it. But any quality system installed by a pro should be able to do that.
Most of them have a panic button control.
Oh, that's a good point. Yeah, you can do that too.
Stupidest panic control, and you just tie into that.
Okay. And I have one more question.
Yeah.
You talk about hacking some of the the keypad locks and stuff like that. They're
Yeah.
electronic. How successful has that been? Is that kind of hit and miss, or has it been repeated a few times? And
Well, so the one we're working on currently is the Hirsch Electronic Scramble Pad. Those are available all over eBay, and they're cheap because they only operate with, guess what, Hirsch Electronic base stations. So we managed to find a rebuilt bare circuit board. That's really the only time you're going to have success, I think, decoding one of those. That particular one had a one-time programmable Intel 8051 CPU that with all the fuses blown so you can't dump the ROM out of it. And it's dead silent until you hook up to this device that sends a 300 hertz pulsing square wave along with some wide pulses here and there for about 5 seconds, and a little green light comes on telling you it's working. So not a secure protocol, but an obscure protocol. And something like a logic analyzer, like the Analogic project from Nullspace, can help you decode that. Now that one also is a little bit unfortunate to decode because it's a 24 volt plus 12 minus 12 signal. So we also need to build some the voltage divider or some protection so that you don't blow up the logic analyzer. But that one we think is doable. Some of the other ones that have a real security challenge response protocol, those might not be so easy, but I think they're all within range of hackability. So does everyone want to put a HID system in their apartment or their garage now? I mean, it's totally doable. It's within range.
How much time did you spend on this?
About half an hour total.
You gonna sell the boards that you guys made?
Good question. Yeah, we actually ordered about a dozen boards, and we have spares and some kits available. So we've been selling those at the 23B shop. We'll be there, Sunday. We'll have some. So we've been selling those for $100 shipped, and we'll sell those for $80 to anyone who attended LayerOne. Anybody else?
And that's just the board, right? You got it. But
No, that's the board and all the components.
the readers too.
No, that would be the board, all the components to stuff the board.
Right.
No Arduino, no readers. The readers are available all over eBay from a lot of China vendors, Hong Kong, Taiwan. They're going to sell for between $20 and $50 each. There's actually a nice little one. It was in the version 1.0. That one will get you both a pin pad and an indoor reader, and it's like $16 plus shipping. It's dirt cheap.
And do you have a mailing list on Google Code project or anything else?
Yes, we do. So there's a wiki at the Google Code link,
Yes.
and that will show you, that reader right there, it's like $16 if you see it. It's totally good.
All right.
But the wiki has a lot of stuff on wiring and debugging and building the thing. And we did find some other information that was interesting. All of the import Asia readers worked fine in our, when we started deploying these. A couple other spaces have them. But some of the expensive commercial brands like HID didn't work reliably. And we discovered they send faster pulses and might be a little bit under spec for what we had thought we'd have. The standard isn't always published. So we figured out there's some workarounds. You can put a couple of capacitors on there, and pretty much any reader works just fine. Really, anything that speaks Weigand 26. If you just do an eBay search for Weigand or W26, you'll find loads of compatible readers and tokens. Yes?
The cloner that you demonstrated, is that the Proxmark project that you were talking about?
That is not a Proxmark. This is a much dumber single-purpose device. And what this does is it lets you simply clone EM4100, 4102 tags. They're one of the cheaper industrial tags that's available, open standards and cheap. But there's no reason that couldn't be done. One other follow-on piece of research, I don't know if anyone reads Hackaday. I know it's 1 or 2 people, right? I don't know if anyone saw the duct tape RFID tag, but someone took just a small 8-pin Atmel CPU. I think it's an AVR 85, and they attached a couple of capacitors and a loop of wire and made basically an RFID tag emulator. And we actually built one of these at the last minute up at the shop last night, and we opened the front door with it after we cloned another tag onto it. So that one will do both the HID cards and the EM4100 because they're very similar. They just use a little bit different encoding. So there's no reason I think that couldn't be extended to other types of cards.
That's why you want to have a pin as well.
Exactly. Yeah, a PIN as well is not a bad idea. It's a second factor. Authentication with integration with an alarm system that has nothing to do with it is another option. That sort of thing. Surveillance, cameras that log off site. All of those, represent defense in depth. Yes?
Would your system integrate into, I know some security camera DVRs have alarm ports on them as well. So could we integrate it into something like that so that it would do the motion detecting as well?
So if it has like a port for a motion detector, that would be a dry contact, and that would be easy to integrate. If it doesn't, there might be other ways of doing it through software. I think we're just about at time. If there's anything else. And these slides should be available online, probably right after the conference. What's that? No reason you can't. I'm just lazy.